Okay, today we're going to move into section 7.2, multiplying and simplifying radical expressions. Let's go ahead and start with the warm-ups. Go ahead and pause and see how you can do. Okay, number one, since the index of the radical was 2 and we are squaring the entire radical, then the radical and the exponent cancel each other out since the index and the exponent match up, and you're just left with x plus 3. Now when the exponent is underneath, remember to be careful. You have to divide the index into the exponent. 2 goes into 2 one time, so I can pull out one of these x plus 3's, but because my index was even, I have to put it into absolute value brackets. And same thing in number 3, the index and the exponent match up, so they cancel each other out. You're just left with y minus 2. Moving on to the lesson. Mainly, all we have here is this product rule of radicals. It says if you're multiplying 2 or more radicals, and as long as the indices are the same, indices is the plural of index, so this index is the same as this index, then I can combine it to be a single radical with that same index, and I can just multiply the radicands. And the restriction is that a and b are non-negative. When we get later in the chapter and we start working with imaginary numbers, then we'll show you what to do there. But for now, just make sure they're both non-negative and you can just multiply them. For instance, in example 1, I'm multiplying 2 radicals that both have an index of 2. Therefore, I can make it a single radical with an index of 2, so we call it a square root, and I just multiply the radicands. And if you actually wanted to FOIL them out, you could use our shortcut, difference of 2 squares, and this is what you'd be left with. Something very important to note here, that many people make this common mistake and they try to simplify this further. They think that they can take the square root of x squared and call it x, or even the absolute value of x, and take the square root of 4 and call it 2. This is wrong. You cannot do that if you have addition or subtraction. You can do that if this were multiplication, and that's basically what this rule is up here. Product means multiplication. So if this were multiplication, then yes, you could do it. It works for division as well, we're going to get to later in the chapter. Addition and subtraction, you can't take the square root of each. If this were multiplication or division, then you can. Letter B. Both of these radicals have the same index of 3, so I can keep that as a cube root, and I can just multiply them to get the cube root of 20. Same thing in letter C. They both have an index of 4, so I can multiply these to be the 4th root of 7y over 5x. And that's how the product rule of radicals works. And we'll move on to the last example to further use that product of radicals. Okay, this is our main objective for the lesson, where we are simplifying radicals that maybe don't have that maybe aren't a perfect square. For instance, the square root of 16 we know is 4. We did that last section. Very easy by now. However, the square root of 20, even though 20 is not a perfect square, this radical can be simplified further. Sometimes they can be. I'm going to discuss 2 different ways that you can simplify radicals further. I will discuss the shorter way first. It's only 2 steps, but it's going to be a little bit harder for some of you. And then I'll take you through a longer way of doing it that some of you may prefer, but it is easier. So the first way to do this, and it is explained up here, we're going to use the product rule. We need to find the largest perfect square that is a factor of the radicand. So if we consider our perfect squares, what are our perfect squares? We need to know this list: 1, 4, 9, 16, and so on. We need to find the biggest number there that goes into 20 evenly. And the biggest one is 4. So I can break this up as the square root of 4 times the square root of, well, 4 goes into 20, 5 times. So I just used my product rule of radicals backwards. Now what is the square root of 4? It's 2 times the square root of 5, and you're done. So as long as you can identify the largest perfect square that goes into 20 evenly, then this is just a 2-step process. Letter B. Square root of 75. The largest perfect square that goes into 75 is 25. How many times? 3 times. Square root of 25 is 5 times the square root of 3. You're done. Letter C. What's the largest perfect square that goes into 72 evenly? Well, some of you may say 9, and that will still work. I will address that because 9 is a perfect square that goes into it, but remember, we need the largest perfect square that goes into 72, and that's actually 36. 36 goes into 72 2 times. So the square root of 36 is 6 times the square root of 2, and that's your final answer. Now let's say you chose 9, which it's not the largest perfect square, but it's still a perfect square. And it goes into 72 8 times. The square root of 9 is 3 times the square root of 8. This is correct. This is 3 times the square root of 8. This is equivalent to the square root of 72. However, it's still not completely simplified because the square root of 8 simplifies further. For instance, 4 goes into 8, and 4 is a perfect square. So I can break this down further into the square root of 4 times the square root of 2. The square root of 4 is 2 times the square root of 2. So you're again left with 6 times the square root of 2. It just took a few more steps to get to it. So when this radicand number gets a little bit bigger, it might be a little harder to find the actual largest perfect square that's a factor, but you can just take it one step at a time and it'll still get there. Let me discuss another way to solve all of these using a factor tree. I know a lot of people prefer this instead of what I just showed you. Okay, if you did a factor tree on 20, maybe you'd do 10 and 2 and then 5 and 2, you'd get that the square root of 20 is 2 times 2 times 5. Now, my index is 2, so I need a factor to occur. I need the same factor to occur twice in order to pull it out. I have 2 2's, so that can come out. I only have 1 5, so the 5 has to stay underneath. So I'm left with 2 times the square root of 5. The next one, 75, if I did a factor tree on it, 25 and 3, 5 and 5. So the square root of 75 is 5 times 5 times 3. My index is 2, so I need 2 of these 5's to come out. And it comes out as 1, it just becomes 1 5. And then the 3, since there's only 1 3, stays underneath. Square root of 72, if you did a factor tree on that, you would be left with 1 2 3 2's and 2 3's. My index is 2, so I have 2 2's. I have 2 3's, so this 2 can come out. This 3 can come out. This 2 stays underneath. 2 times 3 is 6 times the square root of 2. So you can see you get the same answer for all of these as we did using the other method. It's really your choice what you think works better for you. Looking at letter D, again, either method works. If you like the factor tree method, doing a factor tree on 32, you would get 5 2's. The only thing that's different now is the index is 3, so in order to pull anything out, you need the same factor to occur 3 times. So I have 3 2's, that can come out as 1, and I'm left with the cube root of, these 2 have to stay underneath because I needed 3 to be able to pull it out. 2 times 2 is 4. Doing it the other way, you would have to find the largest perfect cube that is a factor of 32. So what are our perfect cubes? Know your list. 1, 8, 27, 64, 125, and so on. The largest perfect cube that goes into 32 evenly is 8, 4 times. The cube root of 8 is 2. You're left with 2 times the cube root of 4. You get the same thing, but again, it was just the 2 steps. Letter E, we have some factoring to do first underneath. I can factor out a GCF of 2. I'm left with I'm left with x squared minus 2x plus 1. That factors further. Square root of 2 times x minus 1 squared. Now I can look at this as the square root of 2. I'm just using my product rule of radicals. Square root of 2 times the square root of x minus 1 squared. Square root of 2 cannot be simplified anymore. It's not a perfect square, and there's no perfect squares that go into it evenly, aside from 1. And here I can divide 2 into 2. It goes in 1 time, so I can pull out one of these x minus 1s, but I must use absolute value brackets. So I get absolute value of x minus 1 times the square root of 2. Typically, you're going to want to write the square root at the end of your expression. Okay, go ahead and see how you can do on these checkpoints. Pause the video, check back to see how you did. Okay, you can check to see how you did. I'm sure you have a few questions on these, so I want to point out a few of the tougher ones, and hopefully I answer your questions. First, if you look at letter D, if you break each factor up using the product rule of radicals, I'd have the cube root of 8 times the cube root of x times the cube root of x to the 4th plus 5. Now, 8 is a perfect cube, so the cube root of 8 I know is 2. These two radicands aren't perfect cubes, nor do they have perfect cubes that are factors. So I can just multiply those. I distributed and combine it to be a single radical. In letter G, I used my factor tree method. You didn't have to do it that way if you didn't want to, but using my factor tree method, I got 10 times the square root of 3. Looking at letters E and F, I did not use the factor tree method. I used the product rule method. I found the largest perfect square or largest perfect cube that went into the radical evenly. In letter I, we had a lot going on with a number as well as some variables, so I kind of broke it up into 2 and took care of each one separately. The square root of 12, you can either use your factor tree method or the product rule method. Either way, you get 2 times the square root of 3. And then for our variables, remember how we handle these. We divide the index into the exponent, and then anything that comes out has to go into absolute value brackets. And then finally, you're not going to want to leave your answer like this. I'm going to want to clean it up and combine everything that's underneath a radical with the same index to be square root of 3ab, and then I put the other stuff in front. And I also wanted to point out letter L. 3 goes into 4 one time with 1 left over, so I can pull out one of the a plus b's, and there's 1 left over underneath. Now make sure that you put this a plus b, since it counts as one factor. It's not going to have absolute value brackets because the index is odd, but you do have to put it in parentheses because this particular factor has 2 terms. If you did not put the parentheses, then this would be interpreted as a plus this product. Order of operations would be taken out, and you would multiply the b times this radical first, and we don't want that. Multiplication would come before the addition, so we have to specify the parentheses that the addition should be taken care of first, and then the multiplication. Okay, go ahead and pause here and try some of these closing questions. Okay, quickly making some notes on a few of these. Number 2 is yes, because all you're doing is you're flipping these radicals around the multiplication, and since multiplication is commutative, this is yes. Number 3, I know you would think yes because -4 times -16 is positive 64. However, if you look back at our rule of the product rule of radicals, these radicands must both be non-negative, and when they are negative like they are here, we have to do something different. We will discuss that later in the chapter. No assumptions must be made in number 4 because you might just have to use absolute value brackets. We don't really care if x is negative or positive. However, in number 5, you can't take the 4th root or the 6th root or the 8th root or the square root of a negative number, so x has to be non-negative. Your homework is in the book 2 through 38 even.